Now, welcome to Electrical Machine 1 lecture. Yesterday or last lecture, in last lecture, we discussed the transformer, three-phase transformer, some numerical based on star delta and some load. So relation between current and voltage, what is the kVA ratings and all these things. Now today, we will discuss all-day efficiency of distribution transformer. All-day efficiency. Of distribution transformer. Distribution transformer is connected to the system and load is continuously varying with respect to time. Say, for example, if you consider the load on transformer, let the load on the transformer is denoted by some curve, and this curve, you know that it is called as a load curve. This load curve may be plotted on the basis of 24 hours. It may be basis of weekly, monthly, and yearly. So this is the load curve. Now, this load curve is plotted between demand in kilowatt or megawatt as per this one. Say we will consider only the load in kilowatt. Okay, so this is the load. And here is the duration or time of the day. Okay, so now let's start from the 6 a.m. Okay, 6 a.m. then 10 a.m. 12 2 p.m. 4 p.m. then it is say 4 p.m. then 6 p.m. 6 p.m. again 10 p.m. 10 p.m. then it is a, say for example, it is 10 and it is again 6 a.m. So somewhere it is a 6 a.m. So this is the 24 hours. This is 24 hours duration. Okay. Now, as if you observe the load on the transformer or in our colony or somewhere, we find that in the morning time the load is small, but it will start, okay, at say 8 p.m. So your kitchenwares started, you are starting in the 10 p.m., 10 a.m. offices and work on, we can say that the shops is going on. Okay, now it will remain up to the 12 p.m. Now during the lunchtime, or say there is some load is decreases, again the load is increases, say at 6 p.m. to 10 p.m. all the commercial buildings, street lights are on condition. So load is highest during that time from 6 p.m. to 10 p.m. and this 6 p.m. to 10 p.m. is called as a peak load even in the power plant distribution area. And after that the load is gone decreasing, and it will after 10 and 11 p.m. the load is very small, only fans and some night lamps are in the working condition. Say this is the, no doubt it is never a like a step curves are there, it is a regular curve, but for our understanding purposes it is shown that it is a step load curves are there, but the load is continuously increasing in the continuous manners. So load is this one. So say for example, this is on the load on the transformer is your 100 kilowatt. Okay, and here it is somewhat more, and here it is somewhat, it is the maximum demand is 150 kilowatt load on the transformer, whereas the minimum load is only say 50 kilowatt. Okay, so the load is not constant, and when the load is not constant, we cannot say that the efficiency of transformer is 90%, because whenever we define the efficiency of transformer is, it is in K, that is, sorry, it is we will represent as a X is the percentage load, it is in kVA into power factor into 10 raised to 3 divided by X into kVA into power factor multiplied by 10 raised to 3, though this term comes into the watt, plus in power, which is given in the say power loss Pi iron loss plus PCU is the copper loss multiplied by 100, so it is a percentage efficiency. But this efficiency is the instantaneous efficiency, means at some particular load condition, say for example, the transformer is loaded at 150 kilowatt, the output of the transformer is 150 kilowatt, whereas the capacity of the transformer, which is given as a in kVA, is 200 kVA. So at particular power factor, say unity power factor, the output of the transformer is 150 kilowatt, and under such condition, it is giving the efficiency is a 90%. But what about the efficiency when during night time from say 10 p.m. or 11 p.m. to 6 a.m. During that time, the load on the transformer is very small, whereas the iron losses will remain present since the transformer is connected to the load. Say this is the transformer. Just I'm representing it as a single phase, but for the distribution transformer, it is a 3-phase transformer where the load is very small, or even say the load is 0. For example, the load on the transformer is 0, where it is connected, remain connected to the source. And when it is connected to the source, the iron losses will remain present. It is irrespective of the load condition. So under such condition, the distribution transformer efficiency cannot be accounted very correctly under such condition. So to define or to evaluate the efficiency of distribution transformer, it is better to represent in the all-day efficiency. All-day efficiency is nothing but the in 24 hours, what is the energy output? Instead of per kilowatt, you just multiply by the time for operation. Here it is multiplied by time. So this comes into the kilowatt hours multiplied by time. Say if just I'm representing this is in kilowatt, so I'm not writing here 10 raised to 3 to convert into the watt. So this power loss also in kilowatt. So multiplied by time. So it is nothing but the energy output in the transformer, energy output by the transformer divided by energy, total energy input to the transformer. This energy input for the to overcome the iron losses as well as the copper losses in primary and secondary winding. Now, remember that in case of the distribution transformer, this energy due to the iron loss will remain present, even though the load is there, even the load is small, even the load is 50% or 0, but the energy loss in the iron losses is going to take place 24 hours because your transformer is going to work. It is remain connected with the source 24 hours, isn't it? So under such condition, whenever the transformer is designed, it is designed at low flux density. Means the transformer is designed in such a way that, for example, if the transformer is designed for a low flux density, definitely the core cross-sectional area is more, isn't it? And when the core cross-sectional is more, definitely the transformer cost is going to increase. But to minimize the cost, someone is going to design the transformer as higher flux density. It will give the more iron losses, because your iron losses, Pi, which is the combination of eddy current loss and hysteresis loss, both are depend upon the flux density. So if the transformer is designed at a higher flux density, that transformer gives the all-day efficiency is smaller, and the transformer which is designed on low flux density, then the transformer efficiency, the transformer all-day efficiency is higher. Okay, so this curve is called as a load. it represent the duration, it represents the variation of load with respect to time. Okay, now this is the kilowatt. Okay, this is in kilowatt and this is in time. So what is the area under load curve? Area, say suppose I'm going to calculate the area under load curve, total load curve. So area under load curve is nothing but, for example, this is the say from 10 to 12, this is 2 hours. Okay, and kilowatt is 100. So 100 kilowatt multiplied by time is 10 to 12, 2. So it is in hours. So it become 100 into, so it become 200 kilowatt hours. So in case, so we can say that what are the different information is available from the load curve? It represents the variation of load, with respect to time. Okay, with respect to time. Second information, it gives the maximum demand and minimum demand. Okay, so what is the maximum demand? Maximum demand is 150 kilowatt and minimum demand is 50 kilowatt. Second information. Third information, average load. Average load means a total load divided by 24 hours is the average load. Fourth point, which is again, it's very important, area under load curve. Area under load curve is total energy. So if it is a transformer, total energy output of transformer. If it is a generator, it is a total energy output of the generator is there. So this is the different information we can collect from the load curve. Then we can calculate the load factor. Load factor is equal to the average load divided by maximum demand. If the load factor is small, it means that we are utilizing the infrastructure very effectively. If the load curve, if load factor is small, very small, it means that the generator or transformer is connected to the load only for a short period of time, and it is not effective use of in electrical installation or infrastructure. Okay, so this is about the load curve of the any transformer which is connected to the distribution in the distribution network. And this load curve is similar for the generator, power plant, and for factory. Again, we can obtain the load curve for the different applications are there. Okay. Now, how to calculate the all the efficiency of the transformer? This is our point to consider. We will take an example on the load, say all day efficiency. Find the all day efficiency of 500 kVA distribution transformer. Say, just we will take a new sheet. What is given? The given is that it is a 500 kVA transformer. 500 kVA distribution transformer. Okay. Whose copper losses and iron losses at full load are 4.5 kilowatt and 3.5 kilowatt. Whose copper losses, first it is the copper loss PCU is equal to 4.5 kilowatt and iron losses is equal to 3.5 kilowatt at full load condition. Okay, at full load condition. Yes, during 24 hours, during a day of 24 hours, it is loaded as under. So here the data is given in the form of say number of hours, then load in kilowatt, power factor, and these three parameters are given. 6 hours. For 6 hours, the load is 400 kilowatt. Okay. And power factor is 0.8. Say 10 hours, it is 300 kilowatt. Power factor is 0.75. Okay. Now 4 hours, it is 100 kilowatt and power factor is 0.8. And for 4 hours, the load is 0 and no power factor at all, isn't it? It means that in the load curve, if it is in the load curve, now here it is not given that what is the time during what time the load is that. So simply it is for the 6 hours. Okay. Next it is a 10 hours. Okay. Then again 4 hours and 4 hours. So load on this curve is 400 kilowatt. After that, the load is decreases to 300 kilowatt for 10 hours. Then again load is decreases for the 10 hours. Okay. And after that, the load becomes 0. So here the maximum load is represented on the left side. This is in kilowatt and it is in time in hours. So such type of curve is curved as a load duration curve. Load duration curve. So it is not the topic to understand topic of the load curve and load duration curve. Just this topic comes here. Now it is not represented here. What is the 6 a.m., 10 a.m. Otherwise, our load curve will be just which we have explained over here. Okay. Now it is for our calculation purposes. This is the such type of loads are there, and such type of a representation of load is called as a load duration curve, where maximum load is represented to the left, then next lower load is to the next to the higher one, and so on. Okay. Now this is the first of all the power here say what is the copper losses at full load? It's 4.5 kilowatt, but it is not remain 4.5 kilowatt. It is different for the 400, and this is different for the 300. It is different for the 100 one. So for that purpose, what we will do, we will calculate the KVA ratings, and from the KVA rating, it is possible to have copper losses. So again, I will write, this is the number of hours, load in kilowatt. Okay, power factor, KVA, load KVA. Okay, it is a load KVA. Okay, then percentage load, we can calculate percentage load, then copper losses. Okay, say for example, this is 6 hours, 10 hours, 4 hours, 4 hours. What is the load? It is 400 kilowatt. It is in kilowatt. Okay, it is 300, 100 and 0. Power factor is 0.8. Power factor is 0.75. Power factor is 0.8 and there is no one. So what is the KVA? So KVA, I write as a KVA is equal to, what is the KVA is equal to? KVA is equal to kilowatt divided by power factor. So here it is 400 divided by 0.8. So it is 500 kVA. So what is the percentage load? The capacity of transformer is 500 kVA, load also 500 kVA. So percentage load is 100%. So here say it is a 100% load. Okay. Now what is the copper losses? During that copper losses is 4.5. So suppose I will write the formula here. It is the percentage load. Percentage load is equal to load divided by load in KVA divided by KVA rated. Okay, it is multiplied by 100 is the. Now copper losses PCU at any load is equal to X square multiplied by PCU. So this is the at any load condition, X square multiplied by full load copper loss, isn't it? So here now 300 divided by 0.75. Now 300 divided by 0.75 is equal to 400. So 400 divided by 500, 400 divided by 500. So it is equal to 80%. Means x is equal to 0.8. So 0.8 square multiplied by 4.5 is equal to 0.8 multiplied by 4.5. So it is equal to 2.88. Okay, so this is the copper loss. Similarly, here 100 divided by 0.8, it is 125 kVA. 125 divided by 125 divided by 500 kVA. So this is the percentage. It is 25% load. So 25%. So it is now it comes around 0.281 kilowatt. Okay. Now here the load is 0% and 0 power loss, isn't it? So when the copper losses is 0, so this one. So what is the total copper losses? Therefore, total CU loss is there. Okay. First we will find the total copper losses in total CU loss energy. Okay. We are calculating the energy. Total copper losses energy is equal to, what is that? It is 4.2 means CU loss multiplied by time 1 CC copper losses. So which is equal to copper loss is 4.5 kilowatt multiplied by 6. Okay. Second copper loss at some particular load condition is 80%. It is 2.88 multiplied by 10 hours plus 0.281 into 4 hours. So this is the total energy loss. Total copper energy loss is equal to it is around 56.924 kilowatt hours. This is the energy loss due to copper losses. Now energy loss due to iron loss. So again it is iron loss multiplied by 24 because transformer is connected 24 hours, which is equal to, what is the iron losses? Rated iron loss is 3.5 kilowatt multiplied by 24 is equal to 84 kilowatt. See here, the copper losses is small. Copper loss is small as compared to the iron loss. So to improve the efficiency, all-day efficiency of transformer, it is quite necessary that during design, the iron losses should be kept as small as possible, isn't it? So this is one parameter. This is second parameter. Yes. So therefore, total loss, so it's total energy loss. Total energy loss is equal to energy loss loss in copper plus energy loss in iron, which is equal to 56.924 plus 84 equals to it is equal to 104, sorry, it is 140, it is 140.924 kilowatt hours. So this is the energy, total energy loss in transformer. Okay, total energy loss in transformer. Now, what is the output? So total energy output. Okay. Now, total energy output. What is total energy output? It is equal to the energy, means power output or load on the transformer multiplied by time. So it is 400 kilowatt for 6 hours, 300 kilowatt for 10 hours, and 100 kilowatt for 4 hours. So total energy output is 400 kilowatt multiplied by time. So we'll write here, it is equal to load multiplied by time. Okay. So load 1, load 2, load 3, and so on, isn't it? Load 1, load 2, load 3. Say we'll write as a load 1 time 1 plus load 2 into time 2, okay, and so on. Okay. So 400 multiplied by, it is running, this load is running for 6 hours plus 300 kilowatt is running for 10 hours, and 100 kilowatt is connected for 4 hours, isn't it? So total energy output is equal to 5800 kWh. This is the energy output. This is the energy output of transformer. Okay. Therefore, efficiency, all day efficiency is equal to total energy output divided by total energy output plus total energy loss. Okay. So here total energy output is 5800 kilowatt divided by total energy output 5800 plus total energy losses is 140.92 kilowatt into 100. So all day efficiency of transformer is 97.6%. This is the calculation of all day efficiency of the transformer. So there are again some numericals. You may calculate some more numericals based on this topic. That is the so only what is the we have to remember that if the load is given in kilowatt, first it is converted into the kVA to determine what is the percentage on load, because the transformer rating is always given in kVA. So from this kVA, it is it can be calculated. That is, a percentage load can be calculated. What is the need of to calculate the percentage load? To calculate the copper losses at different load condition. Iron losses will remain same. Copper losses are going to differ at different load condition. So it is necessary to calculate the percentage load. Once the percentage load is calculated, we can calculate the copper losses at particular load condition, where the X is the percentage of load, is a factor of load, fraction of load, multiplied square, multiplied by the rated copper loss. So here the copper losses for the first 100% load. So the copper losses is 100%. When the copper losses is when the load is 80%, the copper losses get decreases to the 2.88. In the third case, the copper losses at 25% is again is very small. Now next, calculate the energy loss. So kilowatt, it is in kilowatt. Kilowatt multiplied by time is the energy loss. Whereas the iron losses will remain, it is there. Say it represents the copper loss. Suppose it presents the copper loss, whereas it represents the 24 hours. It is up to the 24 hours is the iron losses. Okay. So by this way, efficiency, all the efficiency is determined for the distribution transformer. And whenever you are going to purchase the distribution transformer, see what is the, you just say ask what is the flux density at which the transformer is designed, because higher flux density will decrease the material, iron material, and hence the cost. So it is a competitive rate under the competitive market. The people are going to design the transformer somewhat higher flux density, but during that, because of this one, it will give the more iron losses, which is remain present in the transformer 24 hours. So it is better to purchase the transformer with the low flux density. No doubt the cost of the transformer is somewhat higher, but during due period of time, because of the energy loss, the amount is going to recover. So thank you. We'll stop here.